in this section, we're completely going to focus about, or like we're going to talk about layer 2 forwarding. Cool. So the second layer of OSI model, you can say, which is called as data link layer, it handles the addressing. If you look at encapsulating the traffic after IP address configuration has been done, or you can say after IP details are stacked into the encapsulation header. So the network packets kind of like whenever at network layer, it forms something called packet, right? So the packet
If you
contains
enjoyed the content of the video, don't forget to like and share the video and subscribe to our channel.
source IP address, plus it contains destination IP address, plus it contains whether TCP needs to be used or UDP needs to be used, and plus it contains data from the above layers, be it session layer, be it you can say presentation layer or application layer. That's actually the content of how a packet looks at, like how a packet looks like at layer 3. So when this layer 3 packet is received by layer 2, which is called as data link layer, then the encapsulation stuff forms something called frame, and frame contains source MAC address, plus it contains destination MAC address, plus it contains every aspect of packet, which means it will also have source IP, destination IP, and all these things, right? So you can say that the IP stack kind of then moves on to the frame and then grabs the layer 2 details. Cool. So the layer 2 detail has more to deal about MAC address, okay? And then there are other data link layer protocols as well, which is work. They are very legacy terms, you can say, and are not used that much, like something called frame relay, okay, which is no longer used in the enterprise networks, I would say. And like they kind of completely use the layer 2 addressing method in order to forward traffic. But the focus of, you can say, this particular course would be more on ethernet and wireless technologies, and both of them uses MAC addresses for layer 2 forwarding, so we don't need to take care about the other things that are there. So when we think about something like layer 2 forwarding, then earlier you used to have something called hub, right? So if you have a hub, and let's say there are multiple devices connected, let's say that's user A, user B, user C, and user D. And user A has an IP address like, let's say, 1.1. User B has an IP address called 1.2. You have C as 1.3 and D as 1.4, and they would also have some MAC addresses, let's say like double A, double B, double C, and double D. Now in that case, whenever a communication actually needs to be done, for example over here to over here, so your computer would kind of encapsulate data in a way that source IP address will be 1.1, the destination IP address will be 1.4, the source MAC address will be will be double A, and destination MAC address will be double D. And such type of frame will actually be forwarded to the hub. Now, when hub is going to receive that traffic, how would hub react to it? Can anyone please explain if you would like to?
Yes, I can explain.
Go ahead.
Yes, when a hop receive a frame, he will send it for all the other people, all the other devices.
Okay. And what type of communication do we call it as?
It's a broadcast.
There you go. It's called as a broadcast. So can I say that hub doesn't support unicast and multicast? Because we have three type of communication methods, right? One, we have unicast. The other, you have something called multicast. And then the third one, you have broadcast, right? Unicast is one-to-one communication, multicast is one-to-many, and broadcast is one-to-all. Which means that whenever hub receives this traffic from A, it decides to forward that traffic on here as well, on here as well, on here as well. However, the original recipient of that traffic is only D. So C and B should not receive the traffic that is being sent by A, right? Because A is intending the traffic to only be sent onto D. But hub cannot really do the task of that, right? So why is that? There's like a technical reason to it, right, as well. Now, before understanding why hub doesn't get to like is not able to forward the traffic and all, you need to understand two things. You need to understand what is MAC address, and you also need to understand what is collision domains. Now, I expect that you might have heard about both the terms, right? What's a MAC address and what's collision domains, and you might also have studied it into your CCNA studies. But just to revise it, a MAC address is kind of a 48-bit address split into six octets, right? And you cannot really call it as octets because yeah, they're hexadecimal octets, you can say. So when you think about MAC address, it's again 68-bit of hexadecimal address. Cool, divided into six, and the first three octets are identified as OUI. So if I give you a MAC address like 00:11:22:33:44:55, this is how a 48-bit of MAC address would look like. So half the portion, which is 24 bits, is called as OUI. You can say something like original unique identifier or object or something called as OUI there. Okay, it identifies the name of the manufacturer. Organizationally unique identifier. Yeah, I remember that. So organization's unique identifier kind of helps you to identify that who is the manufacturer of the NIC, of the network interface card, and by that's all gonna be same there. Okay, so a device listens to the network traffic that contains MAC addresses as the packets like destination MAC before moving to the before moving the packet up to the layer 3. So if you have all the like layers as or all the addresses as FF, 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 okay, and then again FF and again FF and again FF, which means like 48 bits of F there. This address is actually used as the destination MAC address for broadcasting. So can we assume that hub just forwards that particular traffic instead of sending it on double D? It's just sending it on all Fs. Can that be a solution, or can that be a scenario in that case? Do you guys think that? Any thoughts on that?
Yeah, I think the help they don't have that knowledge to check the MAC addresses. So he just flood
Mhm.
it all his port.
Okay, and flooding, but so there's a difference now. That there comes another word, right? We have something that is told by you that it is doing flooding. So there is one thing called flooding, and there is other thing called layer to forwarding. These two looks similar in terms of their responsibilities, but they are two different things there. Now we'll talk about the differences there, but that's one approach of how it works. Is there anyone else who would like to say something about my question, that how hub is reacting to it? Is it changing the destination MAC address from the user defined to all Fs? when we say that it's like forwarding all the traffic, or it just does broadcast or something like that.
Maybe hub doesn't build the MAC address table same as switch does, and it just broadcasts the destination MAC address to everyone.
Perfect. That's correct. Well, half of that is correct, I would say. But you can assume that that's correct when you say that hub doesn't really have the MAC address table built up. When we think about Ethernet protocol, okay, or when we think about something like how technologies like ThinNet or technologies like ThickNet, if you have heard about them. These two are like different technologies, and based on these technologies, where they basically get connected with all the network devices using same type of cable and same type of T connectors. Okay, and we basically call them as the thin net as 10 base 2, okay, and thick net as 10 base 5. Okay, which means like they are all ethernet things, and they run on 10 mbps. So that's gonna give you like ethernet connectors there, and you can have RJ45 cables to get connected with these devices. So these two type of like connectivities kind of caused issues. Okay, and the issues were like when two devices tries to talk at the same time, then because the transmitting cable was shared the segment with the other devices and all, the communication kind of halts there, or the cable is sharing the segment with the other device as well, and that's exactly why you would face something called collision. Okay, so to avoid that collision, Ethernet devices use something called CSMA CD, which stands for Carrier Sense Multiple Access Collision Detection, or Carrier Sense Multiple Access Collision Detect. And we use the CSMA-CD technique to ensure that only one device talks at like one time in a single collision domain. Make sense? That's why we do not really like use hub. So if a device detects that another device is transmitting the data, it kind of like sends a jam signal throughout the network with a random timer there, and until that time expires, the device will not actually be able to send any data ahead of it. Makes sense? That's exactly how it works. So this means that devices can only transmit or receive data at one time. Okay, and that like the definition itself, when I say that the device can actually send or receive data at one time, and this behavior is called something like half duplex. You get that? This is what we call as half duplex. So when we think about a topology like this, that you have four different devices connected to the hub, you can say the collision domain is this big. This is what the collision domain is, which means that you have, for example, Ethernet 1 as one of the port there, you have Ethernet 2 as one of the port there, you have Ethernet 3 there, and you have Ethernet 4 there. Now, all of these four ports that a hub has, they are sharing a common collision domain, which means that all these four devices can actually send data at one time, but not all the four devices, they cannot really send data at the same time there. Otherwise that will be kind of something called sorry, that will be something called collision, data collision there. Makes sense. So as more devices are added to a cable or so, the less efficient the network becomes, as devices kind of wait until there is like no communication. So it has to wait until the network kind of becomes idle there. You get that? That's exactly, and that was one of the biggest limitation that previous, like, or you can say old networks have. So all of the devices that are in the same collision domain, the network hubs kind of creates a problem, because they add kind of like, if you add the port density, then it's just like keep on like creating delays for the communication to be delivered. Makes sense, because everyone then has to wait until unless the network becomes idle. If A is sending some data and then when A, until unless A is done forwarding that data, till then network is not idle. So since they are sharing same collision domain, then A will kind of wait until unless sorry, D or C or B will kind of wait until unless A is done sending that particular data, and the network becomes idle there. That's one of the thing that was kind of major limitation. So when this hub was replaced by switch, the switch had an ability to use single collision domain per interface. So if you think of the same topology, and if you replace the hub with something called switch, then what's going to happen is, instead of having, you can say, the single collision domain there, you're going to have collision domain here, 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 and here. So instead of having one collision domain, you now have multiple collision domains. Okay, and you cannot really forward traffic. So what's going to happen in a case that if A is sending the traffic, that's a separate collision domain there, and at the same time D also can send the traffic to the hub, sorry, to the switch. So the switch has the ability to handle both the data at a single time, because the collision domains, the number of collision domains now are increased. But what happens in a scenario when you have a switch there, and then you have user A, then you have user B, and user C is another hub, and then you have user D, and then user C, sorry, the hub has E, F, and G there. So what do you think? How many collision domains are going to be there? Can I say that the number of collision domains are going to be 1, 2,
Level.
and 4? Only 4 collision domains are going to be there. However, the number of devices that are connected over the network is quite bigger. So when you think about that in this approach, you are still sharing a single collision domain in this regard. And this is going to create issue in a way that only E, F, or G will be able to forward the traffic, because hub doesn't have multiple collision domain. If your E and F both try to send the traffic from here and from here, this will kind of be something called collision. And even if switch is placed in the network will still go down. However, there is no collision at this point. The collision is over here at the hub there. That's how it works. Make sense? So when we look at switch, then you understand switch is kind of a device that enhances scalability in a network through creating like virtual channels kind of thing, because this becomes another channel, this becomes another channel, this another, and that is another channel. Okay, and we call these channels as collision. Cool. So a switch also is kind of a smart device, because it has the ability to forward the traffic in all the modes of communication that can actually be done. So switch has the ability to do unicast as well. Switch has the ability to do multicast as well, and switch has the ability to do broadcast as well. Cool. And how does it how does it gets to able to do that? It is able to do that because switch maintains something called MAC address table. So when you look at that MAC address table, it means that a switch might have multiple interfaces, like switch has 0/1, 0/ for example 1, 0/2, 0/3, and 0/4. So if it has all the devices over here, you can say that 0/1 and 0/2 and 0/3 and 0/4 switch will have the list of all the ports that it has the connectivity, or that it physically has there. Okay, and all of these ports are going to be binded with some or the other MAC addresses there. So when the switch kind of initially comes up, the MAC address table is all empty. The switch doesn't really know about any information there. Okay, and instead of flooding the data, switch kind of believes in forwarding the data in like whatever desired way possible. So if a user is looking forward to do unicasting there, it's possible. If the user is looking forward to do multicasting, it's again possible. And if the user is looking to do broadcasting, it is also possible there. That's how it works. So when you think of it in an approach where the switch is forwarding the data, you can say that the A first sends the data to the switch, right? Till here. Now switch when receives the data, let's assume the same scenario that A is having an IP of 1.1, B is having 1.2, and D is having 1.3, where the MAC address is double A, double B, and double D. Cool. So our scenario is going to be in this way, that the source IP address is 1.1 and destination IP address is 1.3 there. Okay. The source MAC address, however, is 1 dot, sorry, I again do the same mistake. And then the destination MAC address is gonna be double D. So in this regard, you can say that whenever we look at something that 0/1 is being used, then as soon as switch receives traffic onto the 0/1 interface, the switch notices that there is the traffic that's coming from it, and it looks into the source MAC address field, and it fills up the information into the MAC address table that 0/1 is connected to a MAC address that's double. But it doesn't really like store the information of destination MAC address, which is double D, into the table, because there is a behavior, and it's like a very strong behavior of switch, and you should note it down as kind of a note there, or an important point, that switch only trusts, sorry for my handwriting, I will clear that up. Switch only trusts on source MAC address. Okay, if you are sending a frame to the switch will not look at the destination MAC address and copy the information in its MAC table. Switch only trusts on the information that is mentioned into the source MAC address field. Makes sense? That's why whenever the switch is going to receive that data, and it's gonna know, probably because of the ARP resolution that might have done earlier on in the PC and all. So the user might know that that's the destination MAC I want to reach to. Okay, but if switch doesn't know about the destination MAC, then what switch is going to do is, switch over here, switch treats such data or such frames something with something called unknown unicast. Okay, switch calls such frames that it doesn't knows about the destination of as unknown unicast. And whenever a switch receives unknown unicast message, it does something called unknown unicast flooding, where it just forwards the traffic out on all the ports that it's connected with, except the port on which it receives the data. Okay, or except the port on which the original frame was received on. So it's gonna forward that particular like a copy of that particular frame to all the other ports, and then it's gonna receive something in a scenario that, hey there, is there anyone who has who has a MAC address double D there? Okay, like that. So it's gonna forward a copy, and whosoever is the original recipient of that particular frame will reply to the switch that, hey there, switch, this particular frame is like it belongs to me, please forward the original copy of that, or like original file of that. And then as the device notifies to switch, the notification is sent to the switch, including like source MAC address as the device's MAC address. And that's when switch kind of adds the information into the MAC address table, that okay, 0/3 is kind of connected to the user who has MAC address double D, and then it forwards the traffic out onto 0/3 port where D is connected with. Make sense what I'm talking about? This is something how switch learns MAC address tables and all.